doing the saddle node model analysis.
The saddle node model consists of two separate equations. One is x prime, one is y prime. The x prime is equal to negative y plus x squared. And the y prime is just equal to negative x plus mu, which is a parameter that can be changed. To find the equilibrium points, super simple. X is going to be y is equal to x squared. To find x by itself, it's just positive or negative square root of y. For y prime is equal to 0, y is equal to mu. So putting that mu in for the y makes it give you two separate abilities for equilibrium points. You have a positive square root of mu, and then a second one, which is a negative square root of mu and mu. We're not considering that negative square root of mu, because you can't have a negative population and be able to accurately get any information from that sort of data. So changing our parameters, if mu is equal to 1/2, we'd get our two equilibrium points to be negative 0.707, 0.5, and positive 0.707 and 0.5. That negative is going to be in this part of the graph, in the second quadrant. And as you can tell by all the arrows, that's just sink. You get a sink, pretty simple. The one in the first quadrant, which is the positive one, which is the one we're considering, you get a saddle. You can also see these are the two null lines. That's for y prime, it's for x prime. And so the equilibrium points are going to be where they both meet. For mu is equal to just plain old 5, the two equilibrium points are going to be the negative 2.2365 and positive 2.236 and 5. Again, two equilibrium points where the null lines cross. One's a sink, one's a saddle. Saddle's the one that we'd be considering if we were going to make a model of two separate populations.
So we can verify our equilibrium point behavior by using the Jacobian. As you can see here, the Jacobian only depends on the x variable. The y was kicked out, taking the partials. So we plug in the square root of mu for the x over here. Trace comes out as 2 root mu minus 1, and the determinant is negative 2 root mu. So this is the general rule for all Jacobians in this system. When mu is equal to 0.5, the trace comes out as 0.414, determinant as negative 1.414. So using the trace determinant plane, this will lie in the third quadrant, which means it's going to behave as a saddle, which verifies what we saw up here. Same thing for when mu is equal to 5, you come out with a positive trace and a negative determinant, which also is a saddle. And now we're going to move on to our representative model. Right here.
All right, so the two populations that we decided to model, one was the amount of dogs in a kennel. And the second is the amount of
Parasites, bacteria.
Yeah, bacteria. Yeah, that cause kennel cough, which is pretty common when you have a lot of dogs in one place. So the Y we chose to, as you can kind of tell, is going to be a population that doesn't change. It's a very constant population within certain parameters. So we chose that our mu is going to equal 4. So that's going to be 4 dogs. As you can see, all of these lines, if we were going to send, instead of going out to 7, if we said it went out to like 500,000, all of those lines would trend towards mu, which means for us, we consider that sort of like a waiting list. So the kennel can only have 4 dogs. If one leaves, another one comes in to fill its place. If a 5th one wants to come in, it's turned away. There can only be 5. Whereas the bacteria is a little more difficult. Instead of trending towards this milk line, it would trend towards this one, which makes sense because the Y is representative of the dogs, where X would be that bacteria. It very loosely follows that null line. If you have less bacteria, they'll trend towards 0. But if you have them past this side, they're going to trend to infinity, and the dog's going to get kennel cough.
Yeah, so basically, as you can see, the trend, we start off with too few dogs. Over time, it's going to trend up to our mu value, which is the kennel's carrying capacity. And if you start above that, they are going to have to get rid of dogs until it comes back to this mu. If we lie on the left side of this null line, that's sort of like an apex point for the disease catching. So if there's not enough bacteria per the dogs, then it's going to trend back to 0 and the disease will die out. But if it does catch, then it's going to spread throughout the population of dogs, and the bacteria population is going to populate into infinity. So that is our presentation. Thank you for watching.